suppose we gave up on sequential consistency. Right, so we said, so solution one, pound in our hardware so that we can keep sequential consistency as our model. You want to know what your program means? Think of every possible interleaved execution of these guys running on a single processor, these two different processes running on a single processor. And I guarantee you that if you run them concurrently on two processors, that whatever happens will be consistent with one of the interleavings. And you say, okay, so that was solution one, and we figured out how to make Snoopy caches do the right thing, so we actually got sequential consistency. Solution two is to say, you know what? Forget that. We're going to adopt a notion of the meaning such that when a particular processor writes a value, every time it reads that processor reads it after that write, it will see the updated value. So there's this notion of a sequence of operations that happens on a particular processor, but there's no guarantee about what other processors see. Right? So we're giving up on this notion of letting everybody agree on the value of a variable. We're just going to say, you're running independently. If you access X and I access X, there's no guarantees that changes that you make to X will be visible to anybody else who's looking at X. And then we introduce, so we say, okay, that's going to be our new model. And then we introduce this new instruction called a memory barrier. Right? And most modern processors have adopted, when we get beyond what a Snoopy cache can handle, now we go to weak consistency and memory barriers. And the way the memory barrier works is it's an instruction that basically goes to everybody and says, please update your memories. Everybody's going to update their memories. After the memory barrier, everybody agrees on the value for all the shared locations. Before the memory barrier, weak consistency, that you could disagree. After memory barrier, you agree. And then there's only certain places in the program where we all have to agree. And it's sort of, so it takes a little work to rethink about how your algorithm should work in the presence of weak consistency and memory barriers. But it turns out you can make fairly large multi-core machines. Machines with tens of cores work quite successfully with this programming model. You just have to change your algorithms a little bit. So, is that a question? Yes?
How do you choose which different values the right one in the memory barrier?
Well, what happens is that if I'm so typically, if you're both randomly changing the same variable, you're sort of it doesn't you haven't clearly come up with a semantics you had in mind. If you change it and I change it, and then we say update it, we have to be prepared to deal with each of our values becoming actually the final value. The real thing is if you're changing something that I later want to share, and we want to make sure that I see your changes, we would put a memory barrier between when you made the change and when I read it. Right, so it's just establishing a certain point in time that we're going to say, okay, you stop changing it and I'll start sharing it. And the advantage of that is that instead of every time you change it, we update everybody. You can make all the changes you want, and then we sort of decide when I'm going to start sharing it, and that's when you put the memory barrier in. So it doesn't solve the problem of two people randomly making changes to the same thing, but the memory barrier makes it very clear semantically when the information is now available for everybody to see. Right? So you get all the advantages of a cache where you can keep changing it, and then at some point you say, I'm done with my calculation, please share with everybody. So you insert a memory barrier instruction, and now everybody else who wants to see that value through we access that shared location will see your latest change. So it works out pretty well.